Okay, we're on. Any questions about this so far? So for anybody watching the tape, a day has not passed. This is only a few minutes. We're taping 2 lectures at the same time. Okay, all make sense so far? All right, now, suppose I wanted to draw the graph, or suppose I wanted to worry about the distribution function, because we started off saying we wanted to calculate FW of t. Well, what's FW of t? If t is 0, of course, it's 0. If t is negative, I should say, it's 0. Remember that this is 1 minus the probability of weighting greater than t. For t greater than or equal to 0, it's given by 1 minus the Erlang c times e to the minus 1 minus rho s mu t. So that's the distribution function. Now notice that if I plotted it, what I get is something like this. There's t, and here is the distribution function. When t is negative, the distribution function looks like this. Here's the value 1. When t is equal to 0, then you jump from this branch to this branch. And if I plug t equals 0 here, I get 1 for the exponential, so I'm left with 1 minus the Erlang c, which is not 0. It's a positive number. So it might be that value right there. That's 1 minus the Erlang c value. And then after that, as t gets larger, this thing approaches 1 asymptotically. So the distribution function has a discontinuity at the origin. So this is a case in which the fact that this is a case in which the distribution function is not differentiable at a point, and that point that's relevant actually. So you have to be careful of that. And in fact, one of the questions they're going to ask you in the next homework illuminates this exactly, because the question I'm going to ask is, find the distribution function of r. In other words, the probability that r is less than or equal to t. Now r, by definition, is the response time, which is the sum of the waiting time plus the service time. I'll get back to this later, but I just want to point out that this distribution function has this discontinuity, and this is W is therefore a mixed random variable. It's neither discrete nor continuous in the undergraduate elementary sense. Now, to find the distribution function of r, I have to take the convolution of w and x. X is the service times, it's exponential, and of course the service times are assumed to be independent of the waiting times. So you have to take the convolution of this random variable's distribution function with this random variable's distribution function to get the answer. And in doing that, if you ignore this jump at the origin, then you're not going to get the right answer. So that's going to be the homework problem. I'll get back to that shortly. Now notice that because the waiting times, the conditional waiting times, are exponentially distributed, that if I were to plot this thing on log paper, that this distribution function, this piece right over here, would turn out to be a straight line. Now some of the questions I want to answer about this, let me go over to here. What about the expected waiting time? All right, so right away I get some formulas here. I find that the expected value of the waiting time, given that the waiting time is greater than 0. I can get that directly from here, because if I know the conditional distribution of w, if I know it's exponential, then I know its expected value is the reciprocal of the thing that multiplies t in the exponent. So in other words, the expected value of w, given the condition, is 1 over 1 minus rho s mu. Or since mu is equal to the reciprocal of the average service time, this is equal to 1 over 1 minus rho times S times tau. Or in units of average service time, it's this piece right here. So that's a nice simple formula. Now what about the unconditional expected value? Well, the unconditional expected value, of course, is equal to the expected value given the condition times the probability of the condition. But of course, this piece is simply the Erlang C. So therefore, you get C of SA divided by 1 minus rho S times tau. So these are nice, simple, important formulas for mean waiting time for those customers who are not served immediately, overall mean waiting time. Here's the total distribution function of waiting times. Now it turns out, as we'll see later, that although this requires that the service, that the Q discipline be FIFO, these are valid whether the Q discipline is FIFO or not, so that makes them a lot more powerful. All right, so maybe what I should do now is just a couple of 1 or 2 more numerical examples. Like, I don't know. What's the probability? Well, let's see. In central office engineering for telephone systems, the Erlang delay model is used as a model of dial tone. So what happens is that when you go off hook, you send a signal to the central office that says that you want something called a dial tone machine. And if you start to dial your digits before that machine is connected to you, then those digits are lost and your call won't go through. Now the dial tone machines are engineered. They're provided on a delay basis, meaning that the way it works is that they assume that dial tone machines will be available quickly. And so they say, let's find the number of dial tone machines such that the probability of waiting greater than 3 seconds for a dial tone machine, or for dial tone, is no more than 1.5%. So when you pick up the phone and start to dial, there's a delay. There's a dead time from when you pick up to actually get the phone to your ear and start to dial. And so if the number of machines provided is such that the likelihood of waiting longer than 3 seconds is less than or equal to 1.5%, the chances are that even if you start to dial without waiting, without thinking about it, even if you're delayed, you'll still get your dial tone machine within the time before you start to dial, and so your call will go through, even though you may not have been aware of this. Okay, so we could estimate something like this. Let's say that we had, I don't know, suppose we had S equals 20 digit trunks, or dial tone machines, as they're sometimes called. So we have 20 of these servers, and how long does it take to, let's see, what would be the average time it takes to dial a call? So we'll take tau is equal to, what, 5 seconds? So it takes 5 seconds to dial a call. So we want to calculate the probability that the waiting time is greater than 3 seconds. Now, 3 seconds, if the service time is 5 seconds, then 3 seconds is 0.6 service times. So what I'm going to do when I make this calculation, what I usually do is I set the average service time to be 1 unit, and then calculate things. That makes everything simple in terms of the program, and then I calculate things in terms of that 1 unit. So in my program, I don't specify the average service time. I just specify the offered load, and then when I specify the time here, instead of specifying in absolute seconds or whatever units the physical problem is, I normalize to fractions of a service time. So here it's going to be, what's the probability that the waiting time is greater than 0.6, 3/5? Okay, so I know how many digit trunks I have. Now, what will be the utilization? Let's suppose that my utilization were 90%. So I'll take rho equals 90%. Now, I don't know what's going to happen. If 90% is going to give me a value greater than 0.015, then I know that my load was too high, and I either have to add digit trunks or decrease the load. Okay, but I'm just making these numbers up. I think they're reasonable, so let's see what happens. Okay, so now I go to my program, and the first thing it asks me is for the number of servers. Let's see, I'll erase this. Okay, so I decided that I had 20 servers here. So I'm going to put in S equals 20. Then it asks me for the offered load. If I have 90% utilization, that means that my offered load would be 18 Erlangs, 18 20ths. So I'm going to put in 18 for my offered load. Then it tells me that the Erlang B would be about 11%. Of course, I don't care about that, but I get that along the way. Then it tells me that my Erlang C value is 55%. So for this case here, the probability of having to wait at all is 55%. 55% of my calls do not get dial tone immediately. Now it asks me for the value of t. In this case, my t is going to be 0.6. So I'll put in 0.6, and then it calculates the probability of waiting time greater than t, and it turns out that that's about 17%. So that's way too high. So I can't do it with 20 trunks, but maybe I could do it with I don't know, 24 trunks or 22 trunks. So let's try it again. Okay, so now I'm going to put in S equals 22. I'll put in my A is still 18. Of course, my offered load is 18 Erlangs. Of course, at 18 Erlangs, now I'm going to have less than 90% occupancy. But that's just the way it goes. Because at 90% occupancy, my probability of waiting was too high. All right, so it gives me the Erlang B is about 6%. It gives me the Erlang C is about 27%. So by adding 2 more servers, I've cut the fraction of customers who don't get immediate service by about half, from 55% to 27%. Now it asks me for the value of t, so I'm going to put in 0.6. And the answer turns out that the probability of w greater than t is now 0.025. So about 2.5%. So from that, I would guess that if I now tried, instead of 22 servers, try 23 servers, I'd probably be all right. Let's try it. So I'm going to put in S equals 23. I'll put in A equals 18. I get the Erlang B is about 5%. I get the Erlang C is about 20%. I put in my T is 0.6. And I find out that my probability of waiting greater than t is 0.009, which is slightly less than 0.015. So 22 is too small, 23 is just right. Okay, so if I had 23 digit trunks and the average service time were 5 seconds, that is, the average time it takes to dial a call is 5 seconds, then the fraction of calls that would have to wait more than 3 seconds until they got dial tone would be, the number that I just read would be a little bit, well, it would be less than 0.015, and 23 is the number of trunks that I need to provide that. So that's an example of a practical problem. Okay? Okay, so now maybe is the time to look at the homework problem. So the homework problem, it says waiting times and response times in MMS. It says consider the simulation programs described in homework 1 and homework 2 for MAP6265 Spring 96 distributed in class. and augment these programs to produce a program that simulates both the waiting times and the response times and yields data that allows calculation of their distribution functions. Okay, so first of all, in homework 1, I gave you this code, and this was basic code that simulated the Erlang loss system. In homework 2, which I just passed out, for the old course, the earlier course, what it says is you're supposed to take the basic code for the Erlang loss system and change it according to the directions here. And if you do that, then you will get code that will simulate the Erlang delay model. In other words, it's the same model except that now when calls are blocked in the previous simulation, they're just thrown away, and now you put them on a queue. So what you should do is convince yourself that if you take this code and you interleave it, the instructions have the appropriate numbers. So if it's a number that wasn't there before, it fits in where that number is. And if it's a number that was there before, then that instruction is overwritten by the instruction that's here. However, when I did that, I asked people to run it, and then what they were supposed to do was they were supposed to check the theory, the simulation results with the theory, and it turned out that it didn't work, or it wasn't as accurate as it should have been. Now, several people took the code that I gave in BASIC and recast it in C, and their answers worked perfectly. But the people who used the code that I gave them, their answers did not work as closely as they should have. So the suspicion was that there must have been a mistake, but obviously there wasn't a mistake in the logic because the people who did it in C used exactly the same logic. They just used different instructions. So I think I found out what the error is, but I'm not sure, so I want you to check it. And here it is. Statement number 350. It reads, if C of I is less than M, then. And the way it originally read was Q equals I and M equals C of I. I think the error was that I should have had parentheses around those, because without it, probably what happens is it does this piece but doesn't do that piece. So the correct version has the parentheses, but I'm really not sure it's the correct version because I didn't try it, but I convinced myself that I didn't need to try it because people who do this kind of stuff are always optimists and always assume that they know what they're doing when they don't. But I have an excuse, which is I don't have to do it. You have to do it. So that's my way out of this. So what I want you to do is I want you to take instruction number 350, and I want you to put these parentheses around it, which is the way I handed it out to you. But I want you to check and make sure that, in fact, the output for the code is sufficiently close, what you would expect it to be, as opposed to the theory. I think what you'll find is if you write the same code and leave the parentheses out, you're going to get a different answer, which is going to be farther away from the theory. So I want you to check that out and make sure that this code is correct. So consider that as part of the assignment. And if it isn't correct, then correct it. So what I'm asking you to do is make sure you understand the logic. I don't want you just to take the logic that I gave you and run it. The idea is to understand why the simulation really does do what it's supposed to do, if in fact it does. Okay, that's what you're supposed to do. Then it says, use this program to simulate MM10 with 90% server utilization. So that means 10 servers, and you're going to have a arrival rate and average service time whose product is 9 Erlangs. Of course, you can fix the arrival rate and the average service time to be anything you want whose product is 9. But my recommendation is, because it says later, it says take the unit of time to be the mean service time and run each case for 100,000 arriving customers if possible. So what that means is if you take the unit of time to be the mean service time, then in effect you're going to take the average service time to be 1. So you have the service times are exponentially distributed with an average of 1, and you make the arrival rate equal, in this case, to 9, and that will then give you 9 Erlangs. And then it asks you to, on a single set of axes, draw the theoretical distribution functions for W and R and plot the simulation values for the values of T indicated in the table below. And it asks you to run each case for 100,000 customers. Now, I'd like you to run for more. If you can run for 1,000,000, then do it. But of course, 1,000,000 is 10 times 100,000, so maybe it'll take too long. But if after 100,000 you've only spent a little bit of time, well then, try 1,000,000. The longer you make the run, the more accurate the answers are. Okay, so here's what you're supposed to get. Here's your table. Here are the values of T. So we're going to take the values 0, 0.5, 1, 1.5, and so forth. Here is the distribution function for W evaluated at T. So in fact, that's what I had written down over here. Let me write it again. FW of T in theory. Okay, now there's two pieces here. There's the theory and there's the simulation. In theory, what you're getting is this. You're getting 0 for T negative and 1 minus the Erlang C e to the minus 1 minus rho S mu T for T greater than or equal to 0. So when you put the entries in the table, the values in the table are calculated from this formula. Except, of course, you're going to set your mu equal to 1. Your S is going to be 10. Your rho is going to be 90%. The T values are going to be 0, 0.5, 1, 1.5, and so forth. And then you just compute it. So you've got to write a program that's going to compute the Erlang C. Okay, then you run the simulation. And in the simulation, what you do is you input these values as input values, and then you count the fraction of customers who wait longer than 0, longer than 0.5, longer than 1. So it's all done in one run. And each customer who arrives has some waiting time. And then, actually not longer, but less, because this is a less than. And so for every customer, you count whether he waited less than each value of T, and then you take the ratio of the number of customers who waited less than that T to the total number of customers, and that gives you the simulation value. Then you're supposed to plot this. Okay, so what the homework is going to look like is this. Here's the graph, and here is the distribution function of W evaluated at T. And here are the values of T. Here is 0.5, 1.5, 2, 2.5, and so on. Here's the value 1, let's say. The theoretical curve is going to be the graph of this, so it's going to look like this. Make sure you put in the whole thing, because I want to see this jump. That's important. And the height of the jump is 1 minus the Erlang C value. And then after that, what you're doing is you're drawing the graph of this formula right here. So in other words, you should get a smooth curve, because preferably the best is if the computer draws it for you, but doesn't have to. You're going to get a smooth curve that's going to look something like that. That is the distribution function. Now when you run the simulation, you're going to print out the simulation values for T equals 0, 0.5, 1.5, and so forth. For say a run of 1,000,000 calls or 100,000. So there's going to be a certain value which we'll put on the graph, which will appear like this, say. That's the simulation value. And then there'll be a value here. Maybe it'll be there. And a value there, and so forth. So what I want to see is the theoretical curve, which is a smooth curve, and then the points are the data points from the simulation. And of course, what should happen is the data points should be close to the theoretical values. and I ask you to actually write numerically to 6 digits, whatever, because that's easy. Whatever calculates out, just put those values in here, copy the simulation values here, so that I'll actually have 2 versions of this. One is the data from which the curve is calculated, and the other is the curve and the simulation output. So I could see the picture of the thing, and I can see exactly what the numbers were, because I can't read the numbers very well from the curve. It'll look very pretty if you use a computer to do it, but you don't have to. I don't care which way you do it. Now, it says, display clearly the formulas used for the theoretical calculations and show your derivation. Now, there's 2 F's. There's this one, and then there's the same thing for FR, theory and simulation. Of course, you don't have to derive this because I already did it for you. But the homework asks you to derive this one. Now, one of the things I've found in the past is that sometimes if you give people a complicated problem, they'll write all kinds of code, but they won't write anything. All you get is this code, which at the time you do it maybe makes sense. But if you look at it a month later, if you haven't actually written down what formulas you're doing, it's not going to make any sense at all. And if you were submitting this to anybody else, you could not just submit code. You have to explain what you're doing. So as part of the homework, if I want you to state explicitly what formulas you're using, write them down using mathematics, and also in the derivation of this, write down the mathematics, write down the formula that you get. And then, of course, when you do that, then the second part says, okay, now, in fact, it says on a single set of axes. So there are going to be 2 curves here. One is going to be for FW, and another is going to be the distribution function of R. So theoretically, you're going to have 2 smooth curves, one for this and one for this. And then there'll be 2 sets of simulation output data. There'll be, at each of these points, there'll be one simulation point that will represent the W and another one that will represent the R. And it would be a good idea for the simulation points to use different symbols, like use a circle for W and a cross for R or something like that, so you can tell which point is simulating which particular value. Okay, now the next question is, how do you find the distribution function of R? Okay, so any questions up to this point? Well, R is equal to W plus X. So that means that the distribution function, what's the distribution function of R evaluated at t? Okay, now I'm going to go through the undergraduate derivation of a convolution. Okay, so this is the probability that R is less than or equal to t. So now I'm going to calculate the probability that R is less than or equal to t. And I'll do that by saying, well, let's see. First of all, I'll calculate the probability that, let's say, X takes the value U, multiply that by the probability that R is less than or equal to t minus U, and then sum over all U. Of course, this doesn't make any sense, but it's suggestive. It doesn't make any sense because X and R are not discrete variables. Okay, so how would I do that? Well, what's the probability that X is equal to U? That would be the density function of X evaluated at U du. What's the probability that R is less, excuse me, I shouldn't have written R here. I should have written W. R will be less than or equal to t if X takes a value U and W is less than or equal to t minus U, because R is equal to W plus X. Okay, so this is the probability that x is equal to u, and now I multiply that by the probability that w is less than or equal to t minus u, which is the distribution function of w evaluated at t minus u, and then I integrate over all values of u. So if I know this density function, I know that distribution function, then I just evaluate the integral, and I get the answer. Of course, I got to get the limits right, and you got to actually implement this. Now, there's another way to do it, because why did I set x equal to u? Why didn't I set w? I could have written the density function of w evaluated at u du, multiplied that by the distribution function of x evaluated at t minus u, and integrated that over all u. What's the difference whether I write r equals w plus x or r equals x plus w? But have to recognize that in this case, what is the density function for w? Well, we know that the density function is a derivative of the distribution function. And the distribution function is discontinuous. Now, it's also true that the density function, that the distribution function for x, which is exponential, is also not differentiable at the origin, but it doesn't have a discontinuity at the origin. So ignoring the fact that it's not differentiable at a point, but is continuous at that point, is not going to have any effect. But if I ignore it here, it is going to have an effect. I'm going to get the wrong answer. So the result is that although I might write down both of these formulas, unless I understand Riemann-Stieltjes integration, which you don't know yet, I can't use this one. I have to use this one. Now, you can try that out. You'll see if you use this one and this one, you get different answers, unless you do this one right, but I haven't told you how to do it right yet. So the way to go is this. And then when you get done, of course, you're going to get a formula which is going to have t in it. And that's the thing that you're going to plot. That's going to be this thing, and that's going to be graphed here. Of course, it should be true that for any t, the probability that r is less than or equal to t is less than the probability that w is less than or equal to t, because r is equal to w plus x. Okay, so r is going to be bigger than w. So the distribution function for for r will lie below the distribution function for the distribution function for r will lie below the distribution function for w. That make sense? Okay, so the homework problem involves, first of all, figuring out this convolution, figuring out this formula, and then drawing the graph of this and this, which is this formula right here, on the same axis. Of course, they're both going to agree for t negative. But then you're going to get something else for r. So you're going to get two curves, and you're going to write down the numerical values that you get from the computation in the column labeled theory. Remember that the curve should be smooth, even though I'm asking you to show your numerical values for specific values of t, namely 0.5, 0.5, 1, 1.5, and so forth, like that. Okay, that's one part. Then you take the simulation and you make sure that this is correct, and you run the simulation to calculate the w's, and you take the values the simulation prints out and you put them as points at the 0, the 0.5, the 1.0, and so forth, and you fill those values in here. And then you also adapt the simulation so that at the same time, not only is it computing w, but it's also computing w plus x to get the response time. And you do that one over here, and again, you compare the simulation value with the theory value being what you got out of here. Okay, so the homework, and then of course you have to graph these curves. And so this should probably take a while. I'm not sure. Maybe make this due in 2 weeks. Is that about seem reasonable?
It's fine.
What?
It's fine.
That's fine?
It's fine. It's fine.
Okay. You're saying fine. Is that F-I-N-E? Okay, good. We're in agreement. Okay, maybe 2 weeks is too long. I don't know. Anyhow, let's make it 2 weeks. So next time we meet, if you have any questions about it, that's the time to bring them up. Important, though, to show all your work, be neat, all that kind of stuff. Okay, any questions? All right, so much for that homework. Okay, the next thing I'd like to do is to go back to the question about the expected value of the waiting times. So we had some formulas. Let's see. We know that for M, M, S, FIFO, we know that the probability of waiting greater than T is the Erlang C times e to the minus 1 minus rho S mu T. And from that, we know that the expected value of the waiting time, given that the waiting time is greater than 0, is equal to 1 over 1 minus rho S times tau. And we know that the unconditional expected waiting time is equal to C of SA over 1 minus rho S times tau. These are all useful formulas. Now, I want to talk about the relationship between the average time you spend in the system and the average number of customers in the system. So now I'm switching gears, and I'm talking about stuff that's in the book on page 178 to 185. Page 178, 185. It's called Little's Theorem. And usually it's written in the notation L equals lambda W. So Little's theorem is going to relate to this stuff here. That's why I'm doing it here. It turns out that there are some theorems in queuing theory that are very powerful, that maybe you could sort of state up front as being major theorems as opposed to just formulas. One of them is pasta, and another one is Little's theorem. And here's what Little's theorem says. Suppose that I have a system. There's a system. And I'm going to put it in quotes because it's flexible in terms of its definition. So I have a system, and I have customers that arrive to the system, and they enter at rate lambda. So lambda is equal to the entry rate. Previously, we've used lambda to be arrival rate. But in Little's theorem, it's just grown up this way, is that lambda is the rate at which the customers arrive and enter the system. And they enter the system, they stay there a while, and then they leave. And while they're there, the average time they spend, by definition, is W. And the average number of customers present is L. And Little's theorem says that L, lambda, and W, assuming that they exist, are linked that way. Okay, so L is average or expected number in system. And W is average time in system. So what you're linking here is two variables, one being a discrete variable, the number present, the other being a continuous variable, the time present. So this is very powerful because, first of all, it doesn't make any assumptions about the system. As long as you're consistent in defining system the same way from the viewpoint of the lambda, the W, and the L, then this is true. So it doesn't have to be a queuing system, or it can be a queuing system, or it can be part of a queuing system. And you don't have to have Poisson arrivals, and you don't have to have any particular, there's no stochastic assumptions about the arrival process, no stochastic assumptions about the length of time you spend in there. It's just customers arrive, they enter, they spend some time, and they leave. And in doing so, they induce an average time present and an average number present, and those things are related this way. So that means that if I want to use this in queuing theory, since numbers like average queue length or average time spent in the queue are important measures, what that means is that I don't have to calculate both of them. If I calculate one of them, then I've got the other. And ordinarily, it's easier to calculate average number, because that's a discrete variable, than it is to calculate average time, because that's a continuous variable. Although in this particular case, we happen to have calculated average time first, because that just fell out. So we can use the average time here to calculate average number by virtue of Little's theorem. Now, the proof of Little's theorem is actually sophisticated, and in fact, it was first proved by Little in 1961, although people knew it for many years before that. And then since 1961, you'd think that, well, that was a long time ago, but nevertheless, people are constantly writing papers on Little's theorem that give simpler proofs or more general proofs, or generalize it to all kinds of different things. So it's actually an area that's still one of active research. In any event, here is the simple-minded, intuitive explanation of Little's theorem, which I think is good enough for our purposes. And argument goes something like this. You say, well, suppose I look at this system over a long period of time. If customers arrive at rate lambda, then over a long period of time t, lambda t on the average will have arrived. So this is the average number of customers who enter the system in time t. And if on the average each one spends W time there, then the total amount of work that is brought into the system is lambda TW. So this is the amount of work that's brought in. You can imagine this is a reservoir in which the work is being brought in, and then the system is using the work up. Okay, now on the other side, how much work is being used up? And the answer is, well, if on the average the number of customers present in the system is L, and each customer is using work up at 1 unit per unit of time, then the total amount of work absorbed, in a sense, by the customers is LT. And then you simply say, well, the amount of work brought in and the amount of work used up have to be the same in the long run, so you set these things equal. Then you cancel out the t's. In other words, you divide both sides by infinity, obviously a phony argument, and you get L equals lambda W. But the formal proof of this, the correct proof of this, is simply, at least one of them, is based exactly on this idea. You just have to make it rigorous and take limits and show that you actually can cancel out that t. But that's the basic idea. Okay, let me hit that argument one more time. You imagine that there's like a reservoir, work comes in and work is used up. And everybody who's present is being worked on at the rate of 1 unit of work per unit of time. So over a long time t, Lambda t is the average number of customers who would enter, and each customer spends a length of time w. So in a long time t, the amount of work brought in on average is the average number of customers times the average amount of work per customer. So this is the total amount that's poured in. How much of it pours out? Well, on average, there are t customers present, and each of them is being served at the rate or using up work at the rate of 1 unit of work per unit of time. So if this is the average number of customers present and that's the length of time, then that's the average amount of work that's used up. So if the amount of work coming in and the amount of work used up are to be in equilibrium, or to be equal over the long run, then you set these things equal, then you cancel out the t on both sides, which was a large number, basically infinity, and then you're left with L equals lambda w. Now, there's practically no assumptions in that, so that's the beauty of the thing. It's very, very general. Okay, so now let me give an example of this. Let's take a look at the Erlang B. Here's an example, just to show that it's right. Okay, so I'm going to take the Erlang B system. Now, we calculated the carried load. By definition, the carried load was the average number of busy servers. So what we did is we calculated Pj, the state probabilities, multiplied by j. And when we did the calculation, what we got was A times 1 minus B of SA. So by definition, this is the average number of busy servers. And by arithmetic, we worked it out and found it to be that. All right, now in my example, to illustrate Little's theorem, I'm going to take the system as being my servers. Okay, so here is my system. So a busy server is the same as a customer. So the average number of busy servers is the same as the average number of customers present. So according to Little's theorem, A prime by definition is L. That's the average number of customers present. Now according to Little's theorem, the way I would calculate L would be I would take the entry rate and multiply that by the average time spent in the system. What's the entry rate? Well, in our notation, the customers arrived at rate lambda. So that lambda is not the same as that lambda. So this is the rate at which they arrived. And then of those, a certain fraction of them actually enter, and the others are blocked and lost. So the Erlang B is the fraction that are lost. So 1 minus the Erlang B is the fraction that enter. So the arrival rate lambda times the probability that they actually enter the system is the rate at which they actually enter the system. So this thing right here, that's the lambda in L equals lambda W. Maybe I should, I'll just say this is the lambda, so I don't confuse that lambda and that lambda. Okay. That's the rate at which they enter the system. Now, once they're there, on average, how much time do they spend there? And the answer is, well, they spend their service time there. How long is that? Well, that's tau. But when you take this lambda times that tau, that originally was defined to be A, and so we get the same answer as before. So in other words, we get the answer from Little's theorem without going through all this arithmetic. Okay, let me go through that again. Here's a direct calculation of the average number in this system, where the system is simply the servers. The average number is simply equal to the probability that there are j times j, and then if you plug in the state probabilities and do the arithmetic, it turns out to be that number, that formula. Okay, now we're going to use Little's theorem. Little's theorem says that the average number is equal to the rate at which they enter times the average time they spend. By definition, the average number A prime is L. How much time does a customer spend in this system if he enters? Well, he spends his average service time. What is the rate at which the customers enter the system? Well, it's the Poisson arrival rate times the fraction of arriving customers that arrive when the system is not busy, which is this thing that I have in this little bracket. Well, that is the lambda in Little's theorem, and since this is the W, then what we have is, since this thing is the same as that thing, that verifies that in fact L equals lambda W. Okay, now I want to go back and I want to use the same argument for MMS, because I want to go from things like this, which tell me average time, to average number, so I get other performance measures. Okay, so now I'm going to, let's see, I think I'll do it here. Okay, so here I'm looking at MMS. So first of all, let me look at the carried load, A prime. Now I said that A prime was equal to A because offered load and carried load are the same. But from Little's theorem, and I said that I could actually prove it by writing out the definition of this expected value. But that's a lot of arithmetic. But it comes immediately out of Little's theorem because I can look at it the following way. I could say, well, here's my system. It consists of those waiting positions and the servers. So I'll make this the system. Now in this system, everybody who arrives enters. So the entry rate and the arrival rate, lambda, are the same. Excuse me, I just made a mistake here in my definition of system. I'm going to make my system the servers only, because remember, A prime is the average number of busy servers. Okay, so if the customers arrive at rate lambda, whether they're blocked or not, everybody who arrives eventually gets served, at least if A is less than S. So we have equilibrium. So that means that the rate at which the customers enter the servers is the same as the arrival rate, which is lambda. Once they get into the servers, the length of time they spend on the average is their service time, average service time, which is tau. Lambda times tau was by definition A, so carried load is equal to offered load by Little's theorem. Okay, now, what's the expected value of the queue length? That is, on average, how many people are in the queue? Okay, so now I'm going to use Little's theorem, but now I'm going to define my system as the queue, not the servers. Okay, so now here's my system. That's my system. My system is just the waiting positions. So by Little's theorem, the average number that are waiting, the average number in the queue, is equal to the rate at which the customers enter the queue times the average time they spend in the queue. What's the average time they spend in the queue? Well, that's the expected waiting time. That's what we calculated over here. What's the rate at which they enter the queue? Well, the rate at which they enter the queue is the arrival rate, because when a customer arrives, he immediately enters the queue. Now, if the servers are available, he passes through the queue in 0 time, and he enters the server. And if a server is not available, then he spends a length of time which is not 0. But nevertheless, I can view him entering and leaving. Nothing in the formulation of Little's theorem says that he necessarily has to pass through in some non-zero time. He could pass through it in 0. That's just part of what's averaged in. So lambda is the rate at which the customers enter this queue, and EW is the average time they spend there. And so lambda EW is the average number in the queue. Okay, so that turns out to be equal to Well, I'll write it here. From this, I get that the average queue length is equal to lambda times EW. If I multiply that thing by lambda, then what I get is lambda times tau, which is A. And when I take that A and divide it by S, I get rho. And so I take that rho and I put it up here. I divide by that 1 minus rho. There's the Erlang C. And so this is the formula for the average number of customers waiting in the queue. Now, I could also calculate this from the state probabilities if I wanted to, but I don't have to. Because once I know average EW, then I get EQ directly from it. OK, so let me go through that again. The argument is that in Little's theorem, I will take the system to be the waiting positions, the queue. And I want to calculate the average number in queue. So I multiply the average rate at which the customers enter the queue, which is the arrival rate, because they can enter the queue and pass through in 0 time if their waiting time is 0. So this is the rate at which they enter the queue. This is the average time that they spend on the queue. We already calculated the average time they spend on the queue directly from the expected, from the formula for the distribution function for waiting time. So we just multiply that formula by lambda. And when you do that, the lambda tau over S is simply rho, and we get this nice little formula. OK, how about the average number in system? Well, the average number in system is the average number in queue plus the average number in service. But the average number in service, by definition, is the carried load. And the carried load, of course, is equal to the offered load. So what we're going to get here is rho over 1 minus rho times the Erlang C plus the offered load. What's the average value of the response time? Well, the response time is the waiting time plus the service time. So that's equal to EW plus tau. EW, of course, is equal to C of SA. Well, I don't need plus, I mean equal sign there. So we get C of SA divided by 1 minus rho times S times tau. That's the average waiting time plus tau. So now you have simple formulas for average waiting time, average queue length, average number in system, which is queue length plus in service, average response time, which is average waiting time plus average service time. Now for MM1, let's see. Let me move this up here. Here's EW equals C of SA divided by 1 minus rho S tau. Now this is for MMS in general. How about MM1? MM1 is the most important single case. In fact, when you take one of these courses in communications and there's any performance in it, all you really see is this formula, the formulas for MM1 over and over again. So MM1 is just a special case with S equals 1. OK, now for MM1, of course, the Erlang C, well, what do we have for MM1? For MM1, I can write this. C of 1A is equal to A. That just comes right out of the formula. And of course, that's the same thing as A over 1, which is the same thing as A prime over 1, which is the same thing as rho. So for the Erlang C, for one server, the Erlang C for one server is the same thing as the server utilization. Okay, the fraction of time that the server is busy is equal to the utilization of the server. So if the server is busy 80% of the time, that means 80% of the customers are blocked. Okay, so with that, then EW takes the form. I just replaced this Erlang C value by rho, and I replace S by 1, and you get this famous formula, rho over 1 minus rho times tau. Or in units of average service time, the average waiting time in MM1 is rho over 1 minus rho. Okay, so if the utilization is 90%, then the expected waiting time is 90 over 10, or 9. Okay, so that's very, very neat. How about the expected value of the queue length? Okay, plugging into this formula and replacing the Erlang C by rho makes that rho squared. Rho squared over 1 minus rho. Another nice formula. How about the average number? Okay, plugging into here, this piece is rho squared over 1 minus rho. This piece is rho. Now, by simple arithmetic, that just writing this rho over a denominator, multiplying numerator and denominator by 1 minus rho, the rho squared term cancels out, and you find yourself with the answer rho over 1 minus rho. And finally, average response time is equal to, according to this, it's equal to rho over 1 minus rho tau, that's that piece, plus tau, and combining these gives you 1 over 1 minus rho times tau. Because this is a classic formula. It says that the average response time is equal to the average service time divided by 1 minus the utilization of the server. Okay, so all of these formulas follow by Little's theorem applied to the general case and then specializing to S equals 1. This is sort of the essence of the quantitative part, the performance part of any of these courses having to do with performance evaluation. Right? Have any of you taken those courses? Right? MM1 all over the place? Okay. Now, something else that's interesting here was I had formulas for the expected value of the waiting time and the expected value of the waiting time given that W is greater than 0. Now, all of those things were derived under the assumption of FIFO. But I said that even though they came from this, and this was derived under the assumption of FIFO, nevertheless, the formulas that I got for here and here are valid whether I have FIFO or not. FIFO is not required for these formulas to be correct, although it is required for this to be correct. And now how do you know that? Well, I know that from Little's theorem, okay? Because Little's theorem says that L equals lambda W. So what this tells me is that any change that I make that doesn't affect L can't affect W either, because L must be equal to lambda W. So what I did was I calculated the W first, and I got the L from it. But now I'm going to argue that the L that I got, in other words, this thing, and do not depend on the order of service. Because if I were to directly calculate the average number present, I would calculate that only from the probabilities that relate to rate up equals rate down. Because average number present comes from the distribution of the number present. And when we calculated the number present, we didn't take any account of the Q discipline. All that mattered was that when I was in a particular state, that that the next guy selected from the queue had the same distribution of service time as anybody else. But it didn't matter which one was selected. So when I talk about the number in the system, it doesn't matter what order I choose them because they're interchangeable. But when I talk about length of time that a customer spends in the system, that does depend on the order because what happens to one customer depends on what I do with the others, whether I take them first or last or put others in front of them or not. So the bottom line is that if I were to have derived this part first, it's obvious that this part doesn't have in it the Q discipline. So this part is insensitive to Q discipline. Now, since L equals lambda W, then this part must also be insensitive to the Q discipline. So even though I calculated this part over here under the assumption of FIFO, I didn't have to. If I had calculated this distribution some other way, of course it wouldn't have been the same answer, but it would have had to have the same mean. So the result, Little's theorem shows then that if I change the order of service, I do not change the average time spent waiting. I don't change any of the average times, but I do change the distribution that produces those averages. Different distributions, but they have the same average. Okay, any questions about that? Okay, so we're sort of finishing up the first course now. Well, halfway anyhow. All right, the next thing I should do, I suppose, is just comment quickly about the quasi-random input and then start talking about queuing networks, which I want to spend some little bit of time on. And then we're going to go into the more advanced material in which we drop the assumptions that either everything is exponential or it doesn't matter whether it's exponential or not. Now, quasi-random input is the model in which I'm still going to have rate up equals rate down, but I don't have Poisson input anymore. Quasi-random input, the idea is that I have a population and it's a finite calling population. By that I mean that ordinarily when you write rate up equals rate down, although I didn't do it before, I should write it like this. I should say lambda j pj is equal to mu j plus 1 pj plus 1. This is rate up equals rate down in general, although I didn't derive this. However, I do derive it in the other course, but I don't want to spend time on that because I want to do other things in this course. Now, Poisson input means lambda j is a constant. That is, this rate does not depend on the state of the system because we imagine that the arrivals are generated by sort of an outside pressure which doesn't know what's going on in the system. However, I might want to take the case in which it does. For quasi-random input, I'm going to try and model the fact of the finite calling population by saying something like this. When I'm in state J, the arrival rate is going to be proportional to the number of customers there are in the calling population. So if the number of customers that are eligible to make calls, that is, imagine that there are n telephone subscribers or there are n terminals, and each terminal is a subscriber in this sense. Then if I'm in state J, the number of subscribers that are eligible to make a request for service is n minus j. That's the number of idle sources. And I'll assume that each of them has exponential inter-request time with rate, say, gamma. So now you imagine that each individual source generates requests for service with rate gamma, that is exponentially when he's idle, but 0 when he's busy. And so that means that when the system is in state J, then J of the customers are either in service or waiting for service, and only N minus J of the subscribers are now eligible to make a request for service. So that means that the aggregate request rate now changes as the system gets more busy. The request rate goes down to reflect the fact that there are less and less subscribers available to make a request. So what that means is that, well, everything is different. I could still solve the equations by going back to here, and instead of replacing the lambda sub j's by a constant, which was easy, I can replace them by this. Mathematically, it's still easy, although algebraically it's more difficult because I've got this other parameter in here. And so I tend to get messy formulas. But another fact is that suppose I look at the system from the viewpoint of the arriving customer. Now I'm going to put an n in here to indicate that I'm talking about the probability the system is in state J just before an arrival instant if I'm looking at a system with n subscribers. So I'm going to make the n explicit. Now, if I were to solve these equations for quasi-random input, where the lambda is given by this, then I would get some answer, and the answer would be given by that. That is, these state probabilities from rate up equals rate down with, I'll put the n in here to indicate that I'm solving them for that particular case. So this is what I get from solving the equations, and this is what the arriving customer sees. We know that if we have Poisson input, by pasta, the pi and the p are the same. But we don't have Poisson input. We have quasi-random input. Poisson input says that the arrival rate has nothing to do with the state of the system. In fact, that's how we were able to derive pasta. But here it does have something to do with the state of the system. So it will turn out that this is not equal. So that's a confusion. What that means is that if I am looking at this, for example, in the computer science context, where these guys are terminals and the server is a CPU, that unless the number of terminals is very large, so that I can consider it to be infinite, that I would be making a mistake if I use MM1 to predict its performance, because I wouldn't have Poisson input, I would have quasi-random input, and everything is different. Okay, now, just to give an idea, I'm not going to go through all this in detail, but I'm going to give a quick idea as to what the pi means. Let's look at the case in which we have n equals 1 source, or 1 subscriber, and s equals 1. Now, here's the state of the system. Suppose I start out in state 0, then the source makes a request for service eventually. Now, how long does it take for him to do that? Well, if his request rate is gamma, then on the average, it takes him 1 over gamma to make a request. When he makes a request, he finds the server idle, because there's nobody else to interfere with him. He holds the server for a length of time called tau. During that time, nobody else makes a request for service because there is nobody else to make a request for service. Then he finishes service and he becomes idle. And when he's idle, then the length of time until he next makes a request for service is again exponentially distributed with an average value of 1 over gamma. So a length of time elapses like that. He makes his request for service. He makes the server busy for a length of time tau, and so on. This process just repeats itself over and over again. So the first question is, what is P1, 1? Okay, that 1 means that I'm talking about 1 source, and this 1 means that I'm in state 1, or the server is busy. And intuitively, I'm going to calculate this by saying, well, look, I have these cycles. They're all statistically identical. So therefore, the probability that the system is in state 1 from the viewpoint of the outside observer is simply the ratio of the average time per cycle that the system is in state 1 to the average length of a cycle. So the average busy period of a cycle is tau. The average length of the cycle is the average idle time plus tau. Or if I multiply through by gamma, I get gamma tau over 1 plus gamma tau. So that's my answer. That's the probability that the server is busy. But what is the probability that the server is busy just before a subscriber wants to use it? What would that answer be? What's the probability that the subscriber finds the server busy when he makes a request for service? 0, right? Can't happen because there's only one subscriber. So the pi's and the p's, or the p's and the pi's, don't necessarily have anything to do with each other. In this model, the fraction of customers who find the server busy is 0, but the fraction of time that the server is busy can be any number between 0 and 1. Okay, suppose I wanted to calculate P2 sub 1. So now I'm calculating the probability that the system is in state 1 in a system in which there are 2 sources, 2 subscribers. All right, so now we'll draw the diagram again. Initially, you're in state 0, let's say, and then somebody makes a request for service. On average, how long does that take? Well, if gamma is the request rate per idle source, then when the server is not busy, there are 2 idle sources. So 2 gamma is the aggregate request rate. So 1 over 2 gamma is the average time. When the request is made, the customer finds the server idle. He makes it busy for a length of time tau. And during that time, if other requests for service are made, then those are cleared. So now I have to make an assumption. I'm going to assume blocked customers cleared. I didn't have to worry about the queue discipline before because nobody was ever blocked. So now I'll assume blocked customers are cleared. So that means that during this time, the other customer may make a request for service. He would be blocked. But eventually, when the server becomes idle again, both subscribers are now eligible to make a request for service, and the average time it would take until one of them does is again 1 over 2 gamma, and so on. So you again get the same pattern repeating itself. So this probability would then be the average busy period per cycle, which is tau, divided by the average length of a cycle, which is 1 over 2 gamma plus tau. Or in other words, 2 gamma tau divided by 1 plus 2 gamma tau. So that would be the answer. Of course, it's different from this answer because this is for 1 subscriber. That's for 2 subscribers. OK, now in the few seconds I got left, I want to calculate pi 1 of 2. So pi 1 of 2 is the fraction of arriving customers who find the server busy. So I'll calculate that this way. I'll say, well, let's take a cycle, and let's see how many customers are blocked per cycle. Well, the only time customers are blocked is when the server's busy. When the server's busy, that means that there is 1 customer making requests for service. If his request rate is gamma, on the average, he will make gamma tau requests. So gamma tau is the average number of calls blocked per cycle. How many calls are offered per cycle? Well, the same gamma tau plus 1, namely the one that makes the server busy. Okay, the p and the pi are not equal. But this pi is the same as that p. Amazingly. Okay, so now the final statement, which I will discuss next time if you want or not, is that I proved right here that pi 1 of 2 is equal to p1 of 1. It can be shown in general, theorem, this is in the book, that in general, if I have quasi-random input, pi j of n is equal to pj of n minus 1. So what that means is when I want to analyze these models with a finite calling population, of which the Poisson input case is actually a limiting case, that I just calculate the probabilities using rate up equals rate down as before, but I replace the number of sources by one less. And I interpret that as what the outside observer sees. Okay, I just want to go do this briefly because I didn't want to skip over it, but I'm not going to spend time on it because I want to get to some other stuff because I'm doing different things in this course than the last course. All right, for as far as reading goes, that stuff is on section, starts in section 3.5. The theorem is stated and proved using my intuitive argument on page 105 and 106, and then a formal proof is given on page 107. And then after that, it's worked out for specific models analogous to Erlang B and Erlang C. Okay, any questions at this point? All right, so next time have your questions ready about the homework, and then I'll start talking about the next chapter because I want to get into queuing networks because I want to talk about output processes. Okay, so that's all, folks, as Woody Woodpecker would